All right, now we're going to move on to the second section of the FRQs from the 2019 AP Calc AB exam. Note that the first two here, problem 3 and problem 4, are the same as problem 3 and problem 4 on the BC exam. All right, so let's get started with number 3 here. No calculator is allowed. So we're given the graph of a function. The first thing I notice here, graph of f. Okay, they tell us f is a continuous function, and it's defined on the closed interval from -6 to 5. So notice that this graph is only from -2 to 5, but the function's also defined, I guess, between -6 and -2. That we just can't see. The figure above shows a portion of the graph of f consisting of 2 line segments and a quarter of a circle centered at 5, 3. They're saying this part here is a quarter of a circle, and that's probably going to be important later. They wouldn't just tell us that for nothing. It is known that the point 3, 3 minus root 5 is on the graph of f. Great. Alright, so part A says, if the integral from -6 to 5 of f is 7, find the value of the integral from -6 to -2 of f. Show the work that leads to your answer. Okay, so remember that integrals, definite integrals, are ones that really are just telling you about the area under the function, between the function and the x-axis, right? And so this integral from -6 to 5 of f of x, well, we don't know what the function does from -6 to -2, but this is really the area from x equals -6 to x equals 5 underneath the function f, or between the function f and the x-axis, right? And they tell us that that's 7. And we're trying to find the area from -6 to -2 of f of x dx. Well, we could break up the big area from -6 to 5 into 2 pieces. First, we could go to -2, and then we could go the rest of the way from -2 to 5. And the sum of these will be the same as the original area. This is going to be 7. This is the full integral from -6 all the way to 5. And so we must be able to compute this piece. And luckily we can compute this as the area of the function f between f and the x-axis. And we can do that because they've given f to us as shapes that we can actually compute the area of, right? So our next goal is going to be in finding this area of the function. So perhaps I'll draw what that area is here in blue on our graph. Remember, the area below the x-axis is counted as negative. Area above is positive. Okay. Because of that, I think the easiest way to do this problem is, instead of computing all of the areas, we could be smart and try to eliminate ones that are going to cancel each other out. So notice that this triangle has exactly the same area as this one, but one's above and one's below, so these are exactly going to cancel each other out. So these kind of just go away. We don't have to worry about them. The same thing is true for this little triangle and this one. Those are also the same, so those are going to cancel each other out. So now we really just need to find the remaining blue area, which from 1 to 2 we can find that as a trapezoid, right? So this is a trapezoid where we have height 1, base. The first base is length 1, the second base is length 3, so 1 plus 3, we do half of our base, we're finding the average of our bases, so we add them and divide by 2, and our height here is this width between 1 and 2, which is 1. Okay, so that's 4 divided by 2, which is 2, and now we need to find this area here. And the key to doing that is to use that it tells us that this is a quarter of a circle centered here. And we know areas of circles, and we also know areas of squares. So to find that dark blue region, I can do the area of this 3 by 3 square, which is 9, and I can subtract off this area of the circle, right? This is a circle with radius 3, and this is a quarter of it, so I'm taking 1/4 of pi r squared, pi times 3 squared. So this is going to be 9 minus 9/4 pi. That's our remaining blue area. So our total area then from -2 to 5 is 2 plus 9 minus 9/4 pi. And so rewriting this equation, we have that the integral we want of f of x dx is equal to 7 minus that whole thing, right? We could simplify this to 11. Minus 11 4 pi. Okay, so this is 7 minus 11 is -4 plus 9/4 pi. Since we don't have a calculator, that is our answer. Okay, great. Let's do part 2. Part B. Evaluate this integral. Okay, so if we're evaluating a definite integral, we're probably going to use the properties of integrals and perhaps the fundamental theorem of calculus. I would say first, let's split this integral into 2 because we have a sum. We can also then pull out this 2 since it's multiplied. So we could rewrite this as 2 times the integral of 3 to 5 of f prime of x dx plus the integral from 3 to 5 of 4x dx, of 4 dx. So I just split that into 2, and I pulled out the 2 here. And now this integral is going to be f of 5, the antiderivative of f prime, f of 5 minus f of 3. And this other integral here, the antiderivative of 4 is 4x. So this is 4x evaluated between 3 and 5. So we need to know what f of 5 is and what f of 3 is. So we scroll on up. F of 5 looks to be 0. F of 3, they tell us 0 minus 3 minus root 5. Careful with your parentheses. Plus, here, remember you always do top minus bottom when you're evaluating. So this is 20 minus 12. And so this gives us, let's see, we've got, if I distribute through the negative and the 2, I have -6 plus 2 root 5 plus 8. So that leads to 2 plus 2 root 5. That's going to be my answer. Okay. Part C says the function g is given by g of x equals the integral from -2 to x of f of t dt. Find the absolute maximum value of g on the interval -2 to 5 and justify your answer. Okay, so this type of problem where you have a function defined by an integral, meaning it's defined using an integral, right? This g is telling us something about the area under the function f from -2 to x, right? And this should be sending off bells in your head about the second fundamental theorem of calculus, which says, let's recall, that says that if you take the derivative of an integral from any number to some other function, maybe I'll call it h, of f of t dt, then this derivative of the integral, integration and derivatives are kind of, they're inverse functions, so they should in some sense undo each other, and they do. What you get is you get f of h of x, so you're plugging h of x in to t for f, but then by chain rule you have to multiply by the derivative of h. Okay, so just a reminder, we're probably going to have to use that at some point here. But what we're supposed to do is we're trying to find the absolute maximum value, so a y value here, not an x value, of g on this particular interval. Remember, absolute maximums of continuous functions, maximums or minimums, can happen at relative maxes or mins or endpoints. So probably what we should do is we should try to find any of the potential places where relative maxes could happen, which would be at critical points. And then we're going to want to make a table to find the value of g at the critical points and at the endpoints and see which value is largest. So recall that relative maximums happen at critical points, and critical points are where the derivative is 0. So our step 1 is to find where g prime of x is 0. So g prime of x of the function g, which is given to us as this integral, which by the second fundamental theorem of calculus up here is f of x times the derivative of x, which is just 1. So this is just f of x. Well, that's good, right? So we're looking for where f of x is 0. We wanted g prime of x to be 0, but g prime of x is f of x. So we go back up to our graph, and let's find where f is 0 on this interval. Maybe I'll get rid of these drawings now so that we can see better. So f is 0 here, here, and here, right? And we're looking for a max, right? So remember, a maximum of, and we have g prime of x is f of x. So a relative max on g would look like this. Its slope here goes from positive slope to negative slope. So our function g prime of x would have to cross from positive y values to negative y values, which happens exactly here. So this is going to be a relative max. This one does the opposite, so it'll be a relative min, so we don't really care about that one. And this is an endpoint, so we're already going to be concerned about that. So our absolute max of g could happen at x equals the endpoint, -2, x equals the relative max, -1, or the other endpoint, x equals 5. So those are the three values that we need to test to plug into g to find what their value is and see which one is biggest. So I would make a little table here. We're trying to find, we have x, we're trying to find g of x. We've got -2, -1, and 5 are the values we're testing. By the definition of g of -2 is the integral from -2 to -2 of f of t dt. I'm taking this x and I'm plugging it in for x. So, but the integral from -2 to 2 is like the area from -2 to 2, which is just 0. There is no area there. So that one's 0. G of -1 is going to be this integral from -2 to -1 of f of t dt, which, again, we have the graph of f, so we can actually compute that area, right? It's this area right here, which is a triangle that has base 1 and height 1, so the area is 1/2 times 1 times 1, or 1/2, right? So this is 1/2. And finally, g of 5 is this integral from -2 to 5 of f of t dt, which, do recall, we computed, I think. -2 to 5, we did that here, right? Don't redo the same work you've already done. We found that was 11 minus 9/4 pi. So this is 11 minus 9/4 pi. And so now at this point you're like, which of these is the largest? And maybe you're not sure which of these is biggest, right? Is this number here bigger than 1/2? That might be hard for you to say, right? But luckily, again, we're interpreting these numbers are just the areas under the function, right? They're the areas under f. And so if you look at the graph, you can tell is smaller than the area that we had computed, right? This blue area was where this 11 minus 9/4 pi came in, right? That blue area is bigger. So this number here is going to be our maximum value. Remember, they don't want the x value where it happens. The answer is the maximum value. This is the max value on that interval. Okay, great. All right, finally, part D. The limit as x goes to 1 of this. Okay, whenever you have a limit, especially a limit at a value, you should try to just plug it in and see what you get. Right? This wants to be 10 to the 1 minus 3f prime of 1 over f of 1 minus arctan of 1. Okay, so let's see. What's the derivative of f at 1? Well, that should be the slope of the function f at 1. So we should go to our function f and find its slope at 1. Here, the slope, it's on a line. I can compute that slope. So slope is 2. So on the top here, it looks like we have 10 minus 3 times 2. That's good. That's a number. And f of 1, I should have checked the value there. F of 1 looks to be 1. Arctangent of 1. Okay, so if we're trying to find the arctangent of 1, let's say I'm going to call this x. This is saying x is the angle that has a tangent value equal to 1. These are equivalent kind of statements, right? So what's an angle that has tangent equal to 1? Well, tangent is where sine and cosine are the same, right? Because sine over cosine would have to be 1, so that would mean sine is equal to cosine. And arctangent also is restricted to the angles between negative pi over 2 and pi. So this happens at where the sine, the y value and the x value of the point on the unit circle are the same, which happens right here at pi over 4. This is where both of these are equal to square root 2 over 2, or 1 over square root 2, whichever you prefer. Okay, so this x value, this arctangent of 1, is pi over 4. And so we could simplify that a little bit. 10 minus 6 is 4 over 1 minus pi over 4. We can leave that like that, I think. This is our answer. Notice, this limit problem was just a direct computation lit problem, right? It didn't involve any L'Hopital's rule or anything like that, which maybe you thought it might initially. But it didn't. So the first thing you should do when you get a limit is just try to plug it in and see if that works, because it might. Really, we're using the function f is continuous and f prime is also continuous at those points to be able to find those. But that's kind of what's going on behind the scenes. All right.
Don't forget to subscribe and hit that bell for all future notifications.